So today we're going to look at circle theorems. That's all about when you draw shapes in or around circles, you might make certain angles, and then sometimes there are relationships between those angles. They might be the same size or some other relationship between them. I'd like to show you some of the most important ones today, and I'll go on and show you all of them. There are 7 of these circle theorems in total. Okay, to begin with, I'd like you to draw some circles. If you have compasses, that would be the best way, but I've just drawn around some sellotape because that's what I have handy. Okay. So for your first circle, I'd like you to draw a chord. Now, a chord is a line that goes from side to side. It won't necessarily pass through the centre, and in fact, please make sure your chord does not go through the centre of the circle, because that chord would be a special case. That's what we call a diameter. What I'm trying to show you still works, even if you draw a diameter, but it's not very convincing if you do draw a diameter. So try to avoid that, please. So you're going to draw a chord. That's a line that goes from side to side, but not through the centre. For example, I might choose it, but you could put this absolutely anywhere you like. So it goes from side to side, but doesn't pass through the centre of the circle. Okay. What I'd now like you to do is choose 2 or more points on the circumference of the circle on the same side of that chord. So for example, I might choose that point there and that point there. They're both on the same side, they're both above the chord. Don't choose one above and one below. You can choose both below if you like, that's fine, but don't choose one above and one below. They must be on the same side of the chord. Remember some other circle names. When you draw a chord, you split the circle into what's called 2 segments. This is called the minor segment because it's the small one. This is the major segment. So minor segment and major segment. You also get 2 parts of a circumference. This big curve that goes from one end of the chord to the other is called an arc. In fact, the major arc here, and this is also an arc down here. This arc is the minor arc. We say the arc is subtended from the chord. Okay, so you've drawn a chord from side to side. That is not going through the centre, so it's not a diameter. And you've chosen 2 points on the circumference. What I'd now like you to do, please, is to create a triangle, or 2 triangles in fact, where this line here is the base of your triangle. Not just part of it, but the whole line is the base of your triangle, and this is the apex of the triangle. So I'll show you what I mean by that. I'm going to connect the very edge. Okay, now this is important. The whole chord needs to be the base, so you haven't got a choice here. It goes, so you're not sort of drawing this and making like a little triangle here. That would be a mistake, a common mistake I've seen quite often, but it would still be a mistake. Okay, so you've got a triangle where the point you chose on the circumference was an apex, and this is the base. Do the same with the other one, like so, and you should find, you can probably guess what happens here, is that these angles at the apex are the same size. I don't know what they are, but they are both the same size, whatever they may be. Now, I said initially that you could choose any points you like on the circumference. I said you could choose more if you like. So had I chosen this one and say this one as well, then it would be the case that these apex angles are also the same size. So any angle that is subtended, is the posh word, subtended by a chord, will give you, it will be the same. Any angle subtended from the same chord is the same. Okay, the same size. This circle theorem has a name, and the name is actually like a description of it. So we say angles in the same segment are equal. I should further point out that you get angles in the same segment even if this chord is not actually visible. So I'll just try to make that a bit fainter, that line. So I hope it's obvious to you that by making that line faint or non-existent, it hasn't changed the size of these angles. The truth of the statement is still the same. Okay. Right, so I'll show you another circle theorem. Same idea again, where I want you to put a chord anywhere, for example here, and once again choose any point on the circumference. It could be, for argument's sake, let's make it the same side that the centre of the circle is on. So the centre of the circle is above the chord, so let's choose a point on the circumference that is above the chord. Okay. I'm now going to do the same as before. I will make a triangle that uses the point on the circumference as the apex, and I'll use the chord as the base. But this time, rather than making another triangle in the same way, I'm going to make a triangle by connecting to the centre. Okay, the apex of the triangle will be at the centre, like so. So we see that I hope you can see that these two angles are not the same size. It seems fairly clear to me that this one is acute and this one is obtuse, and so they can't be the same size. You might have already guessed, it turns out that there is a relationship between the two. This one in the centre is actually twice the size as this one at the circumference. You could say that the other way around. You could say this one is half the size of this one. So what I might do is label this angle as, say, x. It could be any size at all. And this one is twice the size. Okay, x and 2x, like so. You typically recognise this particular one, well, of course, when one is at the centre and one is at the circumference, but you very often get this kind of Star Trek sign sort of shape as well. So it's one to look out for. And much like before as well, if this chord is not actually visible, that doesn't change the truth of the statement at all. So it's still the case that the angle at the centre is twice the angle at the circumference. And in fact, that's the name for this particular theorem. I say this is the name of the theorem, like a little description of it. You do need to know that because very often you give reasons for your answer. So, for example, when you're doing a simpler question, a simpler angles question, you might say something like angle ABC equals 30 because alternate angles, or co-interior, or whatever rule you've used. Angles in a quadrilateral add to 360. So you give some sort of geometrical reason. Same thing here. You might say, oh, angle x is 60 because angle at circumference is 120. So the angle at centre is twice the angle at the circumference. And you can, of course, use the different language here. You can say angle at circumference is half angle at centre. That's perfectly acceptable. And now the next one really is just a special case of the last one I showed you, but the third circle theorem is all about what happens when there's actually a diameter. So I said initially, make sure your chord is not a diameter, and it's partly because you wouldn't be particularly convinced by the thing that I showed you, but furthermore, it's its own particular circle theorem. It's just a special case really, but it is considered the third circle theorem. So draw a diameter anywhere. And choose some points on the circumference. They can be above or below, makes no difference. Same rules as before. You've got to use the chord, the diameter here, as the base of your triangle, and the points you choose on the circumference must be the apex of the triangle. So I'll do a few. So it's totally up to you which ones you chose. You can go above or below or both, it's up to you. But notice how each time I've made a triangle, the angle on the circumference is the apex. Okay, here's another one. And here's another one. I'm not, for example, looking at this triangle in here, okay, because this is not an apex angle in here. Okay, so I'm not talking about this triangle, but any of the others are fine. Okay, what may or may not surprise you then is that the apex angles this time are always 90. That's 90, that's 90. That's 90. I did say that this is just a special case of the previous one, where we knew angle at the centre is twice the angle at circumference, and of course it is. Okay, this angle here is 180. Right, so it's a straight line, or you could say that this angle here is 180. It's just a straight line. So of course the angle at the circumference will be half of that 180. So of course we get 90. And the name for this one is angles in a semicircle are right angles. because this time specifically the segment we're talking about is a semicircle. It's a semicircle above the diameter and it's a semicircle below the diameter, so angles in a semicircle will always be 90. That's as far as we're going to go with circle theorems. We're just doing the 3 today. So that was angles in the same segment are equal. Angles in the same segment are equal. If you have one in the center and one at the circumference, then you've got this double half thing going on, and you've seen the special case, but it is considered the third circle theorem, and that's where the angles in a semicircle will be 90. That is as far as we're going to go, but I just wanted to give you a couple of like warnings and things that you might come across. So just going back to this one for a moment, the simplest case of angle at center is twice the angle at circumference. If I chose the angle at the circumference to be here, so the point on circumference to be here, then I get the following situation where this angle is at the circumference, so it's half the one that's at the middle. It's the same size as this one. Okay, these two angles are in the same segment. But critically, you've got this sort of bow tie shape going on here, and so people will very often mistake it for the first one, where you've got this sort of bow tie shape going on. Okay, I don't know how to easily demonstrate that, but this really is still the second one. This is one angle's at the center and one is at the circumference, and so when it sort of overlaps, you don't get the classic Star Trek sign anymore, but you get the bow tie shape. So it is very often confused with the first one. But simply put, if all of these are on the circumference, then they're the same size. Angles in the same segment are equal. But if one is at the circumference and one is at the center, one at the circumference, one at the center, then you've got this double half thing going on, even if it sort of flops over and overlaps like that. There is one more special thing I wanted to show you about angle at center. So I've drawn any old chord and connected it to the center to make a triangle where one angle is at the center. When we first did this, I said choose your point on the circumference to be on the same side that the center is. So we chose a point up here and we got the Star Trek sign type shape. What if we'd chosen the point on the opposite side to where the center is? So in this case, because I put the chord here, the opposite side to the center is sort of over here. Let's choose this point, for example. But anywhere along here, what if I'd chosen any of these points? Then it's still the case that we've got this double half thing going on. But if this is the angle at the circumference, then it turns out that the thing, when you double this, you get this angle. Okay, I think that makes sense. So this angle here is clearly obtuse, and if you double an obtuse angle, you get a reflex angle, don't you? So I think that makes sense in this case. So it's still the case that if you have one angle at the center and one angle at the circumference, the angle at the center is twice the size as the angle at the circumference. But because the angle at the circumference is on the opposite side of the chord to which the center is on, it's reflex angle instead. Okay, so I've taken you through the first three then. That's angles in the same segment are the same size. Okay, they're equal. Angles where one is drawn at the center and one is drawn at the circumference. If they come from the same chord, you have this double half thing going on. That's still true here. But of course, if it's on the opposite side, it's the reflex angle. And finally, if you have a diameter as your chord, then surely this is a straight line in the middle, which makes 180 degrees in total. So half of that is 90. Therefore, angles in a semicircle have no choice but to be right angles. Okay, best of luck with this.